sklearn, semi-supervised, self-training classifier. Description. The self-training classifier is a semi-supervised learning algorithm in scikit-learn that leverages a small amount of labeled data and a larger amount of unlabeled data to improve classification performance. It follows a two-step process. 1. Initial training. A base classifier is trained using the limited labeled data. 2. Iterative self-labeling. The trained model is then used to predict labels for the unlabeled data. The most confident predictions are then added to the labeled set, and the model is retrained. This process is repeated iteratively until convergence or a predefined number of iterations are reached. Inputs. Bayes estimator. The Bayes classifier, e.g., logistic regression, random forest classifier, to be used for training. This is a crucial input, as its performance directly impacts the overall efficacy of self-training classifier. Unlabeled data. Unlabeled data that will be used to expand the labeled set iteratively. This input is essential, as the algorithm relies on unlabeled data for self-labeling. Labeled data. This input is not directly provided to the self-training classifier constructor, but it is necessary to train the Bayes estimator initially. The labeled data typically comprises features and corresponding labels. Outputs. Fitted estimator. After training, the self-training classifier provides a fitted estimator that can be used for making predictions on new data. The fitted estimator is a version of the Bayes estimator, enhanced by incorporating information from the unlabeled data. Predicted labels. The self-training classifier can return the predicted labels for the unlabeled data, which may be helpful for analyzing the model's performance and understanding its labeling decisions. Steps. Initialize. The algorithm begins by initializing the Bayes estimator with the labeled data. This step establishes a foundation for the self-training process. Iterative self-labeling. The self-training classifier enters a loop, where the fitted Bayes estimator predicts labels for the unlabeled data. It then selects a subset of the most confidently predicted unlabeled instances and adds their predicted labels to the labeled dataset. The Bayes estimator is then retrained with the expanded labeled data. This cycle repeats until a stopping condition is met, such as reaching a maximum number of iterations or achieving a desired level of performance. Metrics. Accuracy. The most common metric used to evaluate the performance of a self-training classifier is accuracy, which measures the percentage of correctly classified instances. However, it's important to note that accuracy may not be a reliable indicator of model performance when data is imbalanced. F1 score. This metric considers both precision and recall, providing a more balanced evaluation of the model's performance on imbalanced datasets. Recall. This metric focuses on the ability of the model to identify all positive instances. It is particularly relevant in applications where minimizing false negatives is crucial. Precision. This metric emphasizes the model's ability to correctly identify positive instances. It is relevant in situations where minimizing false positives is essential. Visualization plots. Learning curve. A learning curve plot can be used to visualize the model's performance, e.g., accuracy on both the labeled and unlabeled data as a function of the number of iterations. This can help identify if the model is overfitting or underfitting the data. Confusion matrix. A confusion matrix visually presents the model's performance by displaying the number of correctly and incorrectly classified instances for each class. It can help identify specific weaknesses in the model's predictions. Fine-tune parameters. Maxiter. This parameter controls the maximum number of self-training iterations. It can be adjusted to balance the trade-off between computational cost and the potential for Further improvement in the model's performance. Threshold. This parameter specifies the minimum confidence score required for a predicted label to be considered for inclusion in the labeled dataset during self-training. This threshold plays a crucial role in controlling the quality of the pseudo-labeled data used to improve the model. K-best. This parameter determines the number of unlabeled instances with the highest confidence scores to be added to the labeled set during each iteration. A higher value may lead to faster convergence but may also introduce noise if the model is making inaccurate predictions. Sampling strategy. This parameter allows you to control how the unlabeled instances are sampled during self-training. For example, you can choose to sample a fixed proportion of unlabeled instances or use a more sophisticated sampling strategy like random sampling or sampling based on confidence scores. Uncertainty methods. Confidence score. Self-training classifier typically relies on the confidence score of a predictions made by the Bayes estimator for selecting the most confident unlabeled instances. Instances with high confidence scores are more likely to have been correctly classified by a model and are therefore more likely to be beneficial for self-training. Entropy. In some cases, entropy-based methods may be used to estimate uncertainty. The entropy of a prediction reflects the diversity of possible labels for a given instance. Instances with low entropy, indicating less uncertainty, are considered more confidently classified and thus more suitable for self-labeling. Challenges and fixes. Challenge 1. Initial model bias. If the Bayes classifier is trained on a limited and potentially biased labeled dataset, it can lead to the propagation of this bias to the unlabeled data during self-training. This can result in the model making inaccurate predictions and ultimately leading to poor performance. Sample use case. Imagine training a classifier on a dataset with a strong bias towards a specific class, resulting in the model's inability to identify instances from other classes. This bias might then be reflected in the unlabeled data, further reinforcing the initial bias. Fixes. Pre-processing prior to training. Carefully consider pre-processing techniques like data augmentation or oversampling to mitigate class imbalance and reduce bias in the labeled data. Model selection. Choose a Bayes classifier that is less prone to bias, like a robust ensemble method or a regularized model. Early stopping. Implement early stopping during self-training to prevent the model from overfitting to the initial bias. Data validation after training. Conduct thorough data validation to identify and address any potential biases in the models. Predictions. Challenge 2. Label noise. As the self-training process involves adding predicted labels to the training set, any errors made by the model during self-labeling can introduce noise into the data. This label noise can further degrade the performance of the model over time. Sample use case during self-training. If the model incorrectly labels an unlabeled instance, this incorrect label becomes part of the training set in subsequent iterations, potentially leading to a cascade of errors. Fixes. Threshold tuning. Adjust the threshold parameter to increase the confidence level required for adding a predicted label to the training set. This reduces the chance of adding noisy labels. Ensemble methods. Utilize ensemble methods that combine predictions from multiple models to reduce the impact of individual prediction errors and improve robustness to label noise. Confidence-based sampling. Prioritize adding unlabeled instances with high confidence scores to the training set, reducing the likelihood of introducing noisy labels. Data cleaning. Periodically evaluate and clean the labeled dataset for potential errors. Removing noisy labels.